us consider a thin spherical shell S of radius r. Let the thin spherical shell be uniformly charged with a positive charge Q. The surface charge density, sigma, is the charge per unit area of the surface, and hence sigma is equal to Q by A, where Q is the charge on the spherical shell and A is the area of the sphere. This can be rearranged as Q is equal to sigma A or Q is equal to sigma into 4 pi r square, since the surface area A of the spherical shell is 4 pi r square. Let this be equation 1. The electric field due to the uniformly charged thin spherical shell has a spherical symmetry. That is, every point on the surface of the shell is at the same radial distance from the center of the shell. The electric field strength at any point is equal in magnitude and is directed radially outward. That is, along the radius vector joining the point to the center of the spherical shell. Now let us apply Gauss' law to derive an expression for the electric field strength at a point P1 outside the spherical shell and at a distance x from the shell. For this, let us imagine a sphere S1 of radius x around the charged thin spherical shell. Here, x is greater than r. This imaginary sphere S1 of radius x is a closed surface and it has area A1 equal to 4 pi x square. The imaginary sphere is the Gaussian surface. The electric flux d phi passing through a very small element of area dA1 of the Gaussian spherical surface S1 is equal to E dot dA1, which is equal to EdA cos theta, where theta is the angle between the directions of the electric field E and the area vector dA. Here, as E and dA1 are parallel to each other, theta is 0. Cos 0 is equal to 1. Therefore, d phi is equal to E dA1. The total electric flux phi is now equal to integral d phi, which is equal to integral E dA1. Since E is constant in magnitude for every point on the Gaussian surface S1, phi is equal to E into integral dA1. Now, integral dA1 is equal to A1, where A1 is the area of the imaginary Gaussian surface S1, which is equal to 4 pi x square. Therefore, total electric flux phi is equal to E into 4 pi x square. Let this be equation 2. We know that according to Gauss' law, the total electric flux passing through the Gaussian surface S1 must be equal to Qin by epsilon naught, where Qin is the charge inside the surface. Let this be equation 3. Here, Qin will be equal to the charge Q on the spherical shell. From equations 2 and 3, we see that E into 4 pi x square is equal to Qin by epsilon naught. Substituting Q for Qin and simplifying this expression, we get the magnitude of the electric field E is equal to 1 by 4 pi epsilon naught Q by x square. Let this be equation 4. Equation 4 gives the electric field strength due to the uniformly charged thin spherical shell at the point P1, which is at a distance x from the spherical shell. By substituting equation 1 in equation 4, we can express the electric field strength E in terms of the surface charge density, sigma, as shown in equation 5. The electric field strength E can be expressed in vector form as E is equal to 1 by 4 pi epsilon naught q by x square into x cap, where x cap is the unit vector along the radius vector and directed away from the charged spherical shell. If the charge q is greater than 0, the electric field is directed outward from the center of the shell, which implies it is positive. On the other hand, if the charge is less than 0, the electric field is directed inwards, which implies that it is negative. Thus, for any point P1, which is considered outside the uniformly charged shell, the electric field due to the shell is as if the entire charge on the shell is concentrated at its center. Now, consider another point P2 inside the charged spherical shell, which is at a distance b from the center of the shell. To calculate the electric field strength at P2, draw a Gaussian surface S2 of radius b. Since the Gaussian surface S2 does not enclose any charge, Q in is equal to 0 for the given surface. Hence, net flux phi through this surface is 0. According to Gauss law, the integral E dot dA is equal to Q in by epsilon naught. Given that the Gaussian surface S2 has a surface area of 4 pi b square, and since Q in is 0 for S2, the electric field strength for any point within the Gaussian surface is 0. Thus, for all distances d from the center of the spherical shell, which are greater than its radius r, the magnitude of the electric field strength E due to the uniformly charged thin spherical shell is given by E, which is equal to 1 by 4 pi epsilon naught q by d square. For all distances d from the center of the spherical shell, which are less than its radius r, the magnitude of the electric field strength E due to the uniformly charged thin spherical shell is 0.